Okay, so yesterday I taught you guys how to achieve linearity, that's what we call it, when we were seeing that a scatter plot was not linear. We were achieving linearity by forcing it to be straight. Now the examples we did yesterday were all exponential style graphs. You could see that there was a curved pattern. So what we did is we used a logarithm to straighten it out, to undo that exponential equation. So there's one other type, we would call that an exponential model, but there is one other type called a power model. So I'm going to get into that today. You'll notice that there's no reading assignment because you did the reading assignment yesterday. Today is the due portion. So you're going to be experiencing exponential models as well as power models in this assignment. So let's get into the example. My dad is an avid fisherman. So every summer he goes to the East Coast to fish for Atlantic Ocean rockfish. He wants to be able to predict the weight of rockfish based on length. So he collects a random sample of rockfish and records their weights in grams and the lengths in inches. I mean, that makes sense. If their length is a certain size, you would kind of expect their weight to be, proportional to that of some sort. So we're curious how this looks. So he did, how many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So he took a sample of size 20, because I have it in 2 rows here, to see what it looks like. So does it make sense to use a least squares regression line of the original data to predict weight? Remember, the purpose of a regression line is to predict stuff. So if I know that it has a certain length, will that predict it well? Well, in order to know if it's wise to use a least squares regression line, we want to know if it's linear. So we need to look at a scatter plot. So I actually already have the data in because it's kind of a lot of data. So if you need to pause the video to type this in, then you can go for it. But I have all of the lengths in my list 1. I have all my weights in list 2. So all I'm going to do is look at a scatter plot. So second stat plot. I'm going to choose the scatter plot option with list 1 and list 2. All right, so I'm going to hit zoom 9. There's my scatter plot. What do you think? Does it look linear? I don't think so. In fact, that looks it looks quite a bit like the graph you were doing yesterday, exponential. I mean, it looks like it's shooting up. It looks like it's evening out as it comes down here. So it does kind of look exponential to me. So let's go over here. Does it make sense to use a least squares regression line? I would say no. The data is not linear. And I'm going to draw a picture. As you can see, they all kind of go right here, and then it really kind of shoots up. It does not look linear to me. So let's try transforming the data using an exponential model, the type of model we did yesterday. Remember, if it looks exponential, let's try to undo the exponential aspect and force it to be straight with a logarithm. So remember, the way we would do that is we're going to come back to our calculator, and I'm going to go to my list, and to try to force it with a logarithm, I'm going to take the log or the natural log of list 2. It doesn't matter which one we do, so I'm going to go ahead and do the natural log. So I'm going to take the natural log of list 2 to try to force it to be linear. So this is just like what we were doing yesterday. When I look at the scatter plot, I'm going to adjust it to list 1 and list 3 now, because list 3 is the natural log, which will hopefully straighten it out. So if I hit zoom 9, well, it straightened it out a little bit, but don't you kind of feel like it curved it upwards this way? So let's again draw a picture of it. Okay, what we did here is we still had the length, the original length in list 1, and we had the weight. But it wasn't just the weight. Remember, we did the natural log of the weight on this side, and that was in list 3 now. And as you can see, the graph still kind of curves, although it curves more upwards this way. And remember, you can always verify if it's curved or not with the residual plot. And I know I'm going to be going through this kind of quickly, but I'm just hoping that you guys remember how to do all these functions in the calculator, so just stop it and rewatch it if you have to. But I'm going to run the regression line on it, which it's asking me to come up with the line anyways. So option 8, I have the newer calculator this time, so I want to do it on list 1 and list 3. Okay, so I'm going to run the regression line, and we might as well write this down now. In fact, I am getting something a little bit different than what my notes say. Okay, even though, yeah, I was getting something different than my notes, but I did just quick double check, and it looks like maybe my notes are wrong. So hopefully you're getting the same values if you typed this in. So what we're trying to do with these values is come up with a least squares regression line. So remember, this is the y-intercept, this is the slope, okay? And so because we took the natural log of the y variable, we're going to put in the y-intercept of 1.115, we'll even round it off to, plus 0.159x. So we write it the same way, we just make sure that we put the natural log in the front. Now, we just ran linear regression. Remember, anytime you run linear regression, it automatically stores the residual. So let's quickly look at a residual plot. Now, I know I'm using a lot of lists here, but I'm going to go over to list 4, and I'm going to put the residuals into list 4. All right, so I'm going to scroll down here. I got a couple other lists in my calculator this time. But there's my list 4. So to look at a residual plot, we got to look at the explanatory, which remember is in list 1, against my residuals, which is in list 4. So when I look at a residual plot, I'm going to say list 1 against list 4. So zoom 9, and I forget that the newer calculators always do that on me. Zoom 9, there's my residual plot. So it's definitely not linear. When it curved upwards like that, when we look at the residual plot, it's definitely not linear. So I'm going to quick draw an example of the residual plot, because it does say show a residual plot next to it. Here's that residual line. Remember that we have the length down here, which is in list 1. That's the explanatory. What we have over here is the residuals, which remember we just put into list 4. I'm trying to keep track of my lists here. It kind of comes up like this and then kind of scoots down like that, something along those lines. But that's definitely showing that this curved pattern here is not linear because the residual plot is very much curved. So, do you think this is a good line to help predict the weight? I don't think so. It's not a line. You only want it to be a good predictor if you can force it to be a line. And unfortunately, taking the natural log did not force it into a line. And even if we did a log, remember the graphs look the same way, even a log would not have forced it to be a line. So the question now, does it make sense to use this least squares regression line of an exponential model drawn above? I would say no. So I'm going to squeeze that in. No, I don't think it would be a good idea. So what else might we be able to do? Well, remember, we took the natural log of the response variables. Any ideas of something else we could do with the natural log? Maybe, just maybe, we should take the natural log of both the explanatory and the response. That's a thought, that's an idea. So what I'm going to do is I'm going to go back to my calculator. Okay, we're going to be playing around with the calculator some more here. I'm going to go back to my list. Now, I'm just going to clear out this stuff for right now. We know that this didn't work, so I'm going to clear out list 3 and list 4. I'm going to go back to the original. List 1 is the explanatory, list 2 is the original response. Okay? So here's what I'm going to do now. Since just taking a natural log of list 2 didn't work, let's take a natural log of list 1 and a natural log of list 2. So I'm going to scroll over to list 3, scroll up. Let's start by taking the natural log of list 1. So these are going to be our new explanatory variables. Then I'm going to scroll over to list 4, and I'm going to take the natural log of list 2. These are going to be the new response variables, but both of these have a natural log attached to it. So let's take a look at the scatter plot of that. If I look at the scatter plot, I want the new explanatories, which is in list 3, against the new responses, which is in list 4. Let's see what the graph looks like. Ooh, man, that looks pretty. The reason I'm liking that so much is it's definitely straight. Look at how straight that is, you guys. So let's go ahead and draw that picture in our notes. Okay? So I'm going to come back to the notes. Let's draw a picture of that. As you can see, it is kind of spaced out here, and then as you get closer, it gets a lot closer together. But remember, to get this axis, we took the natural log of the length. Remember, we put that in list 3. To get this axis, we took the natural log of the weight, which is in list 4. So the original example, the exponential model, just taking a natural log of the response variables, that wasn't enough. But notice, if we took the natural log of the length and the natural log of the weight, the explanatory and the response, it became quite straight. In fact, mine kind of almost looks like it's curved. That's just my sketch. But we can double check with the residual plot. And remember, to get to a residual plot, we have to run the least squares regression, which I want the line anyways. So let's go ahead and run the regression line. Okay? So again, to do that, stat, calc, option 8, linear regression, but we got to do it on the right list. We're going to do it on list 3, the new explanatory, and list 4, the new response. So this is the natural log of the explanatory, natural log of the response. Let's go ahead and calculate it. So this is the example, or this is the new y-intercept and the new slope. In fact, look at how that regression is. Look at how pretty that is, 0.999. That's almost 1. That's really, really good. So think carefully about how we would write this. You know that before, when we took the natural log of y, we wrote that we took the natural log of y. We wrote the y-intercept, negative 4.374, and then plus, we would write the slope. The slope is 3.049. But then up here, we wrote just the explanatory, but we don't use just the explanatory anymore. What we are using is the natural log of the explanatory. So you want to, again, input the natural log into that space. So we took the natural log of the response, we took the natural log of the explanatory. We still write the equation the same, we just have to indicate where we took the natural log. Last but not least, we can quickly show a picture of the residual plot just to make sure there's no curves. So again, if I do that, remember, because I ran the linear regression, my residuals got stored for me. So I'm going to go back to my list. I'm going to go all the way over to list 5. Again, keep track of these lists, okay? And I'm going to plug in the residuals. So list 5 is my residuals. And now remember, we are going to do the new explanatories against the residuals to find a residual plot. So in my residual plot, I'm going to keep the explanatories I got going, the natural log of the explanatories, with my residuals, which I now have in list 5. I hope you're keeping track of these okay. So let's take a look at that scatter plot. That is a nice random scatter. That's exactly what we want to see in a residual plot. So let's go ahead and sketch that picture. Here's my residual line, and as you can see, there's just kind of there's a lot of random scatter. So remember, we took the natural log of the length, which was in list 3, and we took the natural log, or no, this is the residuals, which is in list 5. Okay, my time's about to run out on my 15-minute video, so see the next video for the very last little piece of this.